Okay, let's finish off. This is basically our last chapter. It's stuff we already know, so it's just more equilibrium stuff. So, and actually, this first part is stuff you definitely know. It's Le French guy, Le Chatelier. So, okay, let's say we have a solution of acetic acid, which is a weak acid, right? So when you put that in water, right, you have your acetic acid. You put that in water. It's a proton donor. It produces hydronium and acetate. So here's our acid. There's the conjugate base to our weak acid here. From what I told you, you guys should know that if I add something that's involved in this equilibrium, it's going to shift the equilibrium to the opposite side. So if I were to add hydronium to this system, it's going to push the equilibrium back towards the reactant side. If I add acetate to this system, it's going to push it back towards the reactant side. So common ion effect is basically something you already know. It's Le Chatelier. So let me get to the actual thing here. It says that the extent of ionization of a weak electrolyte is going to be decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. So if I go back to the slide, right? If I add sodium acetate or potassium acetate or calcium acetate or like anything acetate, that's going to increase the acetate concentration. And remember that your Ka expression, right? If you actually write out your Ka expression, it's going to be the concentration of H3O times concentration of acetate all over the concentration of the acetic acid. That's a constant. That ratio, that expression, it doesn't change. So if I go in there and I increase this, the system is going to use up that extra acetate that I put in there, and it's going to make more of this to keep that balance. So in a weird way, the acetic acid here is going to be less ionized. There's going to be more of this intact stuff in there than there was before I added the acetate. All right, let's mess around with an example. And let's calculate the fluoride concentration and the pH of a solution. So this is all one solution. I'm not adding one thing to another. This is all in one big thing. So it's 0.2 molar HF and it's 0.1 molar HCl. All right, so I have the Ka for my HF, which is my weak acid, hydrofluoric acid. That's 6.8 times 10 to the minus 4. And if you write out the whole Ka expression, that should equal your hydronium concentration times fluoride concentration divided by your HF concentration. That all has to equal 6.8 times 10 to the minus 4. That's your constant. This question is having us calculate the pH, so we need the H3O plus, and it also wants us to calculate the F minus, which is right here. So we need these two things, and we're just going to bust out a nice table. All right, so you write out your equation. Yeehaw, HF, H2O, H3O, F minus. There's going to be a little bit different though. So when we do our ice, the initial concentration of the HF, that was 0.2, that was given to us. Our hydronium, this H3O plus, this is not 0, all right, because we had HCl in our container. We had 0.1 molar HCl, and so 0.1 molar HCl is actually going to give us 0.1 molar hydronium and 0.1 molar chloride, but chloride is a spectator, and it's an ion that doesn't have anything in common with this up here, so we don't care about it. So we just care about the H plus. So the initial concentration of the hydronium is 0.1 molar. Our initial concentration of F minus is 0, but now we just do things as usual. The change, when we change our stuff there, it's just going to click. Let's see. Sweet. It's going to go down by X. The H3O goes up by X. The F minus goes up by X. X is really small. I know that because my Ka value is times 10 to the minus 5. It's a really small thing. This HF does not ionize much. So 0.2 minus X is still basically 0.2. 0.1 plus X is still basically 0.1. 0 plus X, that's going to be X. And that's the X we're going to solve for. So we huck that into our Ka expression. So 6.8 times 10 to the minus 4 is going to equal 0.1 times X divided by 0.2. Math, math, math. That tells me that X is 1.4 times 10 to the minus 3. X was our fluoride. All right, so our fluoride concentration is 1.4 times 10 to the minus 3. Cool, I'm halfway done. The other part of the problem, I wanted the pH. All right, so to get the pH, I need the hydronium ion concentration. It was 0.1. Now that I've actually calculated X, I could add X to 0.1, but you see, it really actually doesn't do anything. So when we ignored it before, that's justified, right? It doesn't change it. So our concentration of hydronium was 0.1. So you take the negative log of 0.1, it tells me that the pH was 1. Piece of cake. Here's some homework. Yeehaw. So 13, 14, 15. 15 is going to be doing, it's like a B, and C. parts A, B, and C. Knock those things out. It should be a piece of cake. It's just like the example I just worked. The part C is a little bit tricky. Don't forget on part C, you're actually mixing two different solutions, so you're gonna have to account for the dilution. But it's should be pretty easy. All right, good luck.